All right, we are very happy to have Bhola Nath Saha from IIT Kanpur, and he will be speaking on filling with separating curves. Yeah, over to you, Bhola.
Yeah. Thank you, Shomoda, and I want to thank the organizer for giving me the opportunity to present my work here. So I will be today I will be talking on filling system or filling with separating curves. This is a joint work with my supervisor, Dr. Bidyut Shanki. Oh, okay. So, a quick overview of today's talk. First, we'll discuss some preliminaries that will be essential in this talk. Then we'll see some motivation of starting filling system, and then we'll see some recent developments in this direction, and at the end, our contribution. So let us start with a closed orientable surface HG. By classification theorem of surface, we know that HG is either a sphere or torus or connected sum of sphere with tori. A simple closed curve on a surface is an embedding of the unit circle. In this picture, alpha is simple and beta is not. Now we define geometric intersection number. So given a pair of simple closed curves alpha and beta, we assign a non-negative integer called geometric intersection number, and it is defined by this relation. Here, tilde stands for free homotopy relation. And we say that the two curves alpha and beta are in minimal position if the geometric intersection number between them is same as the number of points of intersection between the curves. In this picture, the geometric intersection number between the curves alpha and beta is 2, and also the curves are in minimal position. Now we define filling systems. A collection of simple closed curve is called a filling system if the curves are pairwise, non-homotopic, and they are in minimal position, and the complement of the union of the curve in the surface is disjoint union of topological disk. Now, if the number of curve is 2, then we call it a filling pair. And if the number of disks is minimal, then we call it minimally intersecting filling. So here in the torus, the meridian and longitude, if we cut the torus along meridian and longitude, we get a square, which is a topological disk, and hence they form a filling pair. So consider so here we have a genus 2 surface, and consider the curves alpha, beta, gamma, and delta. Now, if we cut the surface, we get a disk, a polygon, which is a disk, and hence the curves alpha, beta, gamma, and delta form a filling system on S2. Now define topological Morse function. So let us start with a real valued continuous function f on an on an n-dimensional manifold M. We say that a point x0 of M is called an ordinary point of the function f if locally the function f can be expressed as a coordinate function, and the point x0 is called critical point if it is not ordinary point. A critical point is called non-degenerate if locally it can be expressed by this equation for some coordinate chart, and the function f is called a Morse function if it has only finitely many critical points and all of which are non-degenerate. Now we see an example of Morse function. So consider the unit sphere in the in R3 and consider the height function. So then this function is a Morse function that it has two critical points, the North Pole and the South Pole. Now we define mapping class group. The mapping class group is collection of all orientation preserving self homeomorphism on a surface modulo isotropy. Note that if the surface has non-empty boundary, then this homeomorphism fixes the boundary pointwise. There are some example of mapping class group. The mapping class group of this is identity, and the torus is SL to Z, and mapping class group of annulus is Z. Now we'll see some motivation of studying filling system on surfaces. The first one is construction of pseudo-Anosov map. Note that pseudo-Anosov map are the most non-trivial mapping class group elements. So Pinar has shown that for this we let us take two multi-curves A and B such that A union B fills the surface. Now suppose TAJ denotes the Dehn twist around AJ, then the function f, which is composition of TAJ and TBK inverse, where each AJ and BK occurs at least once, is a pseudo-Anosov map. So another motivation is due to Thurston. Thurston has claimed that the set chi-g of those surfaces in the techular space which admits a filling set of systolic geodesic construct a spine many things about the set is still unknown, for example contractility, dimension, connectedness, etc. So now we'll see some recent developments in this direction. The existence, combinatorics, topology, geometry of minimally intersecting separating filling pair are extensively studied by WoG, Huang, Sankey, Minasco, Niland, and by many more. Jeffries, Fanoni, Parlier further extended the study of minimally intersecting filling pairs to punctured surfaces. Now, the mapping class group acts on the set of minimally intersecting filling pair as follows. Suppose F is a member of mapping class group and alpha beta is minimally intersecting separating filling pair, and the action gives F alpha F beta. So Ogo Huang have studied combinatorics of this action. Ogo and Huang also defined a function fg on the moduli space which which gives the shortest which is defined as follows: for a hyperbolic surface x, so fg of x is the is the length of the shortest minimally intersecting filling pair on the surface x. So they have shown that this function fg is a Morse function, and the growth of the set of global minima of fg is exponential, which now we have seen that most of the work we discussed are in most of the work the curves considered are non-separating. In our work we also allow separating curves. So let us start with the definition of separating filling pair. So a curve is called separating if the complement is disconnected. Now, a filling pair is called a separating filling pair if at least one curve in this pair is separating. So a separating filling pair is called minimal if the number of disks is minimal, that is 2. Now here is an example of minimally intersecting here is an example of separating filling pair. So consider the curve alpha and beta. Here if we cut the surface along these two curves, we get four polygons. So two octagon and two quadrilateral. So that's why this alpha and beta is a first of all filling pair, and since alpha is separating, so this is a separating filling pair. Now a question arises. Suppose we are given a filling pair. So how to deduce that this filling pair is separating or non-separating? So the two so we have answered this question in our first result. So the main ingredient to prove this is fat graph theory. So fat graph means a graph with some ordering at the with some ordering at the edges emanating from each of the vertices. So here we can see that at each vertex, so this is a four valence graph, and the orientation of the surface gives a ordering on the edges emanating from each vertex. So we have drawn this vertex. So we have drawn this graph here. This is the graph, and also we have maintained the same ordering and as in this surface. So this is called fat graph. This is the rough definition. I have not given the exact the precise definition. Now, so the ordering is something like that. So here we have here we have x1. So here we have x1 in this direction, and in this direction y6 inverse. So in this direction we have x6 inverse, and in this direction this is y1. In this way we get a permutation. We get a cycle of order 4 at each vertex. So we have wrote down this written down this ordering at each vertex, and using this cycle we get a matrix which is called normal matrix, which we call normal matrix. So in this matrix we just put the row of this matrices consists of this cycle, and we put in such a way that all the xi's are in first column and the remaining columns are determined. So we can see that in the second column y6 and y6 inverse are in both are in second column. Similarly y2 and y2 inverse are in same column, and also this thing happens in column 4. So we can so therefore note that the edges xi stands for the separating curve, and here we have placed the separating curve, the edges representing the separating curve in first column, and this thing happens. And in the second column, if yi is there, then yi is also inverse is also there, and also this holds in fourth column. So observing this particular example, we have proved a general result. So the result is follows. Suppose we are given a fat graph with two standard cycles, x1, x2, xn, and y1 with yn. The cycle alpha is separating if and only if yi and yi inverse are in the same column of the normal matrix M of alpha beta for every I equal to 120. And the proof is in the same way as in the example. I have not included the proof due to time constraint. Now, a question is does there really exist a minimally intersecting separating filling pair on a surface? So answer is yes. uh, uh, so we have shown that there exists a minimally intersecting separating filling pair on SG if and only if G is even and G is greater or equal to 4. The proof of existence is by inductive construction. So for G equal to 4, we have constructed this particular example, and for G equal to 6 and for G equal to 6, we have taken a suitable genus to surface, and we attached this surface with the genus 4 surface, and we get genus 6 surface with minimally intersecting separating filling pair. So in this way we get for G equal to 8, 10 and so on. And we have also shown that for G is equal to 2, there exists no minimally intersecting separating filling pair. That means number of disks in the complement is 2. No such pair exists in genus 2 and also in genus odd genus. Now, so as in the case of so the mapping class group also acts on the mapping class group also acts on the set of minimally intersecting separating filling pair, and we have shown that the number of orbits of this action of this mapping class group action satisfies this inequality. Now, so as in the case of minimally intersecting filling pair, so here we also defined a function fg on the moduli space, which gives the shortest the length of shortest minimally intersecting separating filling pair. So we also we have shown that this function fg is proper and a Morse function. Furthermore, for so furthermore we have given a lower bound a lower bound of the function fg, which depends only on the topology of the function. It does not depend on the geometry of the function, and we have shown that this fg is greater or equal to mg, where mg is the perimeter of regular right angled 4g cone. And also we have shown that the set bg that consists of those hyperbolic surface at which the function fg uh, takes the value mg. This cardinality of this set is same as ng, where ng is given by this. That is, ng is number of mapping plus group orbits of minimally intersecting separating filling pair. So this so these are some references. Thank you.
Thank you, Bhola, for the very nice talk. Any questions from the audience? Could you please show the references page again? Yeah. All right. Let us thank the speaker. Thank you very much, Bhola.
Thank you, everyone.